Welcome back to the workshop once again for more comparisons of series. Today we want to take a look at the limit comparison test to determine if a given series converges or diverges. Alright, so when we want to look at the limit comparison test, we need to have that the terms are all positive. So in each of these cases where n is positive, both of these are positive. So there's no issues there. And then once we have that, then we can choose a series which we know converges or diverges to help us demonstrate that the given series either converges or diverges. Again, if we have the limit as n goes to infinity of a(n) over b(n) is equal to some number where that number is greater than 0 but less than infinity, then we can conclude that both a(n) and b(n) converge, or both a(n) and b(n) diverge. That is the series of those terms. Excellent. In the first case, we'd like to say to ourselves, does this converge or does this diverge? And it actually works out to be the case that this, let's see here, should converge. So what I'd like to do is I'd like to compare this to, or compare the terms, right? I need a bn or an an. Put it numerator, denominator, doesn't really matter. 1 over n squared. And what I would like to do, the reason that I'm choosing 1 over n squared is because my numerator is 1, that's the same. But then if my denominator, if I didn't have the square root, or if I could take the square root of n squared, I'd have n times n. I just have this extra plus 1 to deal with, which isn't really doing a whole lot to our overall value, especially as we get large values of n. So if I could take the square root, then I have n times n, which is n squared. So I suspect that this is going to act similarly to 1 over n squared. So I'm going to take the limit as n goes to infinity of, I'm going to take this guy first. It doesn't matter what you write on top and what you write on bottom. Just whatever you happen to copy down is fine. N squared plus 1 over 1 over n squared. Of course, when I divide by a fraction, that's the same as multiplying by the reciprocal. So this is equal to the limit as n goes to infinity of 1 over n times the square root of n squared plus 1 times n squared over 1. And I'm going to leave it to you to use appropriate techniques for evaluating limits, but you should find that this limit is equal to 1, if I remember correctly. So they both act in the same way. Let's see here. So we chose 1 over n squared because we believe that it acts similarly to this, and this happens to be a p-series that converges. So our conclusion would then be, since the limit, actually here, we already showed that the limit is finite, so since the sum from 1 to infinity of 1 over n squared converges by the limit comparison test, the sum that we're interested in, the sum from n equals 1 to infinity of 1 over n times the square root of n squared plus 1, this also converges. Excellent. So you might suspect that in order to have some well-rounded examples, that the next example should diverge. Let's see if we can figure that out. I would encourage you to pause for a moment, and if you believe it diverges, find a series which you can compare this to, use the limit comparison test, to show that this diverges. So find a divergent series in which the terms, when we take the limit of the ratio, will give us a number L, right? Larger than 0, less than infinity. So feel free to pause and do that. All right, so if you did that, that's fantastic. If you did not, that is fine. We are actually going to find that this is a series that converges. So again, if you would like, if you tried to find a series to compare it to for divergence, you didn't find anything, or what you found was unfortunately not correct, but this does converge. And if you'd like to take a moment to find a series to compare it to, that would be a fantastic idea as well. If you're not going to do that, that's fine. We can observe that when n gets really large, this isn't doing a whole lot right here. So effectively, the only thing we have is 1 over 2 to the n minus 1, right? As n is really large, n over n plus 1 approaches just 1. So this would be 1 times something, essentially. So we want to compare to the terms, a series with terms that has 2 to the n minus 1 as its terms, right? These are the terms of the series that we want to compare it to. So we take the limit as n goes to infinity. Now I'm going to start off by taking this and multiplying by the reciprocal of that, just to save ourselves some work. So this is, well, you know what, I better not do that. Let's take it as n over n plus 1 times 2 to the n minus 1 divided by 1 over 2 to the n minus 1. Let's just do that so that way we can make sure that we are on the same page at all times. So this is the limit as n goes to infinity. That is, in order to use the limit comparison test, we are always taking an and dividing it by bn. Whichever is your an and bn, that doesn't matter. All right, so limit as n goes to infinity of n over n plus 1 times 2 to the n minus 1 times 2 to the n minus 1 over 1. Of course, the 2 to the n minus 1s will cancel out, and the limit of n over n plus 1 is just 1. So again, we have a limit which is non-zero and finite. This is where we want to be careful. Since the sum from n equals 1 to infinity excuse me, of 1 over 2 to the n minus 1. Now this looks a little bit different than something we're familiar with, but this is actually a geometric series. If we were to adjust the indices a little bit, we could let this be k. So take k from 0 to infinity. And if we start at 0, then instead of subtracting 1, right, because I subtracted 1 to get there, it would just be k in the exponent. 1 over 2 to the k converges. So since this converges, it is a geometric series. By the limit comparison test, the sum that we're interested in, or the series that we're interested, the sum from n equals 1 to infinity of n divided by n plus 1 times 2 to the n minus 1 also converges. Excellent. So I think the interesting, or the part that might be a little bit difficult at first while you're developing your ability to apply the limit comparison test, or even the direct comparison test, is to recognize what series to compare our given series to. So we compared in this case to 1 over n squared, we compared in this case to 1 over 2 to the n minus 1. And what I'm trying to do is I'm trying to look at this series and observe what it looks like. In this case, when I take the square root of n squared, I end up with 1 over n times n, which is 1 over n squared. Right? I'm ignoring this plus 1 because it doesn't do as much. Here, n over n plus 1 almost cancels out. Right? So if I were to take a look at that, then I could see that those essentially cancel out, leaving me with just that, so that's what I'm comparing it to. That is how I'm making my choices of what series to compare the given series to. All right, one additional comment on which method works better, the direct comparison or the limit comparison test. And it's really just a preference. Sometimes it's easier to see one over the other. I enjoy the limit comparison test quite a bit because there's a little bit more flexibility here. The direct comparison test can be difficult sometimes in terms of manipulating rational expressions to find a different rational expression that's either larger or smaller to justify the whatever convergence or divergence you're claiming. So in both of these cases, if I were to, for example, since I know that this converges, I've already shown that, I could use the direct comparison test for this. So what I could do is, let's see here, I could try to I could try to decrease my denominator to end up with a larger fraction. And if I were to do that, I could decrease my denominator by removing this plus 1, and in which case I would have 1 over n times the square root of n squared, or 1 over n squared. So I could actually use the direct comparison test with exactly the same series. Similarly here, I could use the direct comparison test. I can increase the overall value of the fraction here by simply adding 1 to the numerator. By adding 1 to the numerator, I now have the cancellation of n plus 1 in the numerator and denominator, which leaves me with exactly this. So again, I could also use the direct comparison test with exactly this series. Now, will it always work out that you can use the direct comparison, or the limit comparison with the same series that you would have used the direct comparison? That's not necessarily the case. If you were to return to the video where we discuss the direct comparison test, you would find that in the series we discussed there, so we discussed there the series sum from 1 to infinity of 1 over n factorial, and we compared that to the series of 1 over n squared. If you were to use the limit comparison test, you would not find that there's a finite non-zero limit. You would find that there is actually either 0 or infinite limit, depending on which way you arrange those terms. All right. I hope I was able to provide a little bit more understanding of the limit comparison test. Of course, you're always welcome to search for additional examples. I'm sure that other people are providing examples as well. I hope you guys have a great day, and I look forward to seeing you again soon in the workshop.